All right, we're back. We're on page 291, and let's get going. So we're going to talk about a very fundamental concept, one of the more important, it's going to stay with you forever type concepts, the tangent line. And we've already dealt with this a little bit, right? If you think back, I don't know, a page or so, you'll see that, well, where is it? More than a page. Up here. Here we go. These are some tangent lines, right? So we found the point on the curve, we found the slope, the derivative at that point. We had to use the limit definition of the derivative to do that. So that was the limit as h approaches 0, f of a plus h minus f of a all over h. Or we could have used, we are now finding out, the limit as x approaches a of f of x minus f of a over x minus a. Either one, they give the same result. And then we just wrote the line in point slope form. So that's basically what we're going to do here. So close your eyes because I'm zooming a lot. Here we go. Maybe. Whew, that took a while to catch up. All right, so assume that f is differentiable at x equals a. What does that mean? So differentiable means, it means that f prime of a exists. Kind of like a, it's not the most exciting thing, but if a function is differentiable to a point, it means the derivative exists at that point. So we could find that limit, evaluate it, we'll get a finite number. So that's what it means for it to be differentiable. Tangent line to the graph of y equals f of x at the point P, a comma f of a, is a line through P with the slope f prime of a. We already know that. Write the equation of the tangent line in point slope form. All right, so this is going to look weird. It's like the only time in your life. Well, no, there's an application of tangent lines where you will use this. But for our purposes, this is probably the only time you'll do this. So it's y minus the y value, right, which is f of a, equals the slope, which is f prime of a, times x minus a. That's it. That is your point slope form. Now we're always going to be using point slope form because when you use point slope form, you can see the point of tangency. That's the idea. I look at this and I can see right away that the point of tangency is a f of a. I can see it by looking. It's like with parametrics, you don't want to reduce too much. When you're finding volumes of revolution, you don't want to reduce delta x too much. You just don't want to reduce because you lose information when you do that. And we don't want to lose information. We want all the information we can possibly have. Find the equation of the line tangent to the graph f of x equals x squared at x equals 3. Show all work. Okay, so I need to find, I'm going to need f of 3. But since f of x is x squared, so it's just going to be 9. I need f prime of 3. So that's going to be, let's use the limit as x approaches 3 of f of x minus f of 3 over x minus 3. All right, so what work will that be? Limit as x approaches 3. F of x is x squared minus 9 over x minus 3. So far, so good. This looks like a limit that I know how to evaluate. If I plug in 0, if I plug in 3, I get 0 over 0. So I'm going to do some algebra stuff. So the algebra stuff I'll do here is factor limit as x approaches 3 of x plus 3, x minus 3. I don't think anyone would have a problem with you stepping this particular skip, I think is what I was going to say. Skipping this particular step because it's pretty much expected that you can factor that. We get this. Okay. And then I plug in and I get 6. All right, not bad. And then I want to write the equation of the tangent line. So it's going to be y minus the y value, which is 9, equals f prime of 3, which was 6. That's the slope. And then x minus 3. So this is my tangent line. And so I should probably label it. There we go, tangent line. Based on the shape of the curve, if you use your tangent line to approximate f of 3.02, would you get an over or under estimate? All right, let's think about this curve. So the curve is x squared. So let's draw it. All right, so this is f of x equals x squared. And then we're going to put a tangent line at x equals 3. So I'll use a different color. So let's say this is 3. And then our tangent line, look at that. So you can see the tangent line is below the curve. So we're going to get an underestimate. So I'm going to say that, since the tangent line is below the curve. So you do a lot of like writing, a lot of explaining. Since the tangent line is below the curve, the tangent line approximation is an underestimate. I mean, how could it be anything else? Ooh, I made a circle and I can't delete it. This happens a lot. I should learn how to delete these. Can I erase it? I can erase it. I can't delete it, but I can erase it. That's weird. Is an underestimate. Okay, so when you're looking at a curve, you can tell right away if a tangent line will give an over or underestimate just based on the location of the tangent line. So because the tangent line is below the curve, so let me write this. Tangent line below curve. Does that say curve or does that say cure? I think that says cure. Below the curve, C-U-R-V-E. That's a weird looking word when you spell it halfway, mess up, and then try again. If the tangent line is below the curve is concave, C-O-N-C-A-V-E, up. So we know that this curve is concave up because the tangent line will always be below it. Like take a tangent line, put it anywhere, you'll see that it's going to be below. All right, let's use a calculator to see if this is true, if we get a thing that we're expecting. So give me 1 second to get this going. Calculator page, here we go. Okay, so new document, I guess. Calculator, f of x is x squared. All right, so if I plug in f of 3.02, I get that, whatever that is. The tangent line told me that it should be 9 plus 6, the quantity, 3.02 minus 3.02 minus 3, 9.12. So 9.12 is less than the value of the function, but like, look how close they are, right? So this is the magic of tangent lines. They're really easy to evaluate by hand even, and they're very, as long as you're close to the point of tangency, you're going to be very close to the value of the function. That's one of the main uses of tangent lines, is you can use them to approximate things. All right, I'm just going to keep going on this. You know, if this is too long for you, you can pause it and come back. You can watch it at double speed, see what I sound like there. You can, I don't know, do whatever you want, you know, free country, live your life. All right, let's see. Sketch a graph of f of x equals 1 over x plus 1. All right, so that, I know that's 1 over x and then shifted 1 unit to the left. You want to know those things. So I'm going to put the asymptote in red. There we go. And then I'm going to use black for the curve. So 1 over x should look like this. So like I'm thinking of 1 over x and I'm just shifting it. So I know that there's a horizontal asymptote at 0, right? Horizontal asymptotes, where those come from, limit as x approaches infinity, and the limit as x approaches negative infinity. This is a rational function, so they will be the same. But if it was not a rational function, could be some stuff going on. All right. Based on the sketch, do I think that f prime of 0 is positive or negative? All right, so at x equals 0, I'm like here. I see that the curve, like just imagine it. Imagine putting in a tangent line. In fact, why imagine? I'm going to do it. This is a terrible graph though, because I'm realizing at 0, I should have gone through 1. So what I'm going to do is I'm actually going to erase it and do it again, because it'd be better if it was kind of accurate. Let me see. Let's do a better job. We're better than this. Let's see. Here's a point. Okay, so I'm going to go through that. You know what I did? I did the classic thing. I tried to get to the asymptote too fast. That's a student's common error, and sometimes teacher, it turns out. Okay, this is better. It's really, my graph from 0 to infinity is really not great. It's hurting. All right, so we were looking at 0, which we said was right here. All right, imagine or actually draw in a tangent line. So I'm going to dot in a tangent line. Why would I dot it? I'm going to draw it. I mean, part of the reason you would dot it is that it's easier to dot in a line than it is to draw a straight line, but whatever. Okay. Based on that line definitely has a negative slope. So I'm going to say f prime of 0 is negative. And I can see that the tangent line has a negative slope, but a better reason for that would be to say, because f of x, whoa, where are we going? F of x is decreasing at x equals 0. So if a function is decreasing at a point, its tangent line will have a negative slope. The function will have a negative slope. If a function is increasing at a point, its tangent line will have a positive slope. The function will have a positive slope. So being able to tell if the slope is positive or negative also tells you if a function is increasing or decreasing. Huge connection. We're going to talk about that a ton. Find the equation of the line tangent line at x equals 0. All right. We got to find. We already, well, we kind of know that f of 0 is 1. So f of 0 is 1. We're going to need f prime. So I'm going to say that f prime of 0 is, let's do the limit as x approaches 0 of f of x, 1 over 1 plus x, or x plus 1, one of those, minus f of 0 is 1 over x minus 0. X minus 0 always looks weird, but write it that way, you know, because otherwise it looks even weirder. So we've done a lot of these, so I'm just going to go for it. Common denominator in the numerator gives me 1 minus the quantity x plus 1 divided by x times 1 plus x, which I kind of put in a weird place because I wasn't really thinking about spacing that out. So this is the limit as x approaches 0 of, so I get 1 minus x minus 1, so negative x over x, 1 plus x, limit, I still got to write limit because I'm still writing x, negative 1 over 1 plus x, negative 1. Whew, okay, so that was a slope, but then I need the tangent line. So therefore, the tangent line is going to be y minus the y value is 1 equals the slope, and then x minus 0. So you might not like writing that x minus 0, but you should do it. Point slope form is a very, you look at it all the time, you get used to it. Just do it. Do it like a machine. Don't like think about it. Use your tangent line to approximate f of 0.2. Okay, approximate, right? So if we are, that was really thick. If we are approximating something, then we're not getting the exact value. So we should make that clear. So f of 0.2 is approximately, so if I plug into the tangent line, I will get 1 minus 1 times 0.2 minus 0. So 1 minus 0.2, which is 0.8. All right, and then we're asked to find, or approximate, f of negative 0.2. So f of negative 0.2 is approximately, it's going to be 1 minus 1 times negative 0.2 minus 0. That's 1 plus 0.2, so that's 1.2. All right, so approximating values of a function using a tangent line, just take the x-coordinate and plug it in. That's a pretty straightforward thing. You're asked to do it all the time. Like approximating a function is one of the main uses of calculus, especially what's called differential calculus, the part that involves taking derivatives. So we're going to be doing it a lot. All right, let's look at our graph. Which of these do you feel is more accurate? So I have no real way of knowing what you're saying. I'm going to say my answer is I think that the approximation at 0.2 is more accurate than the approximation at negative 0.2. My reason for that is look how fast the function is changing. Let's use a highlighter here. As I go, that's a gross color. Okay, so as I go to the left from 0, start here, go like this, the function is changing rapidly. So it's going to peel away from its tangent line really fast. Whereas if I go to the right, the function itself is actually leveling off. So it's not going to peel away very fast. It's going to take a little longer. I mean, it's definitely peeling away, but it's not going to peel away as fast. So I think, I'm going to say, I think that the, what should I say? The approximation at x equals 0.2 is better because the curve, I'm going to say the curve peels away. Peels? P-E-A-L-S? Poles? Let's use poles. I'm not even sure. Peels. Oh, man. Pulls away from the tangent line less quickly in that direction. So this is not a rigorous formal thing, but I think it's good enough. All right, now, should we use a calculator to see which one was better? I think we should. I'm going to switch, and then I'm going to wrap this video up. This one's, I feel like this is a long video. All right, let's see. I'm going to define f of x to be 1 over 1 plus x. I think it's 1 over x plus 1, but because of the sum of an infinite geometric series, I always think of that as 1 over 1 plus x instead of 1 over x plus 1. Later in your life, you will also do that. All right, let's see. F of negative 0.2. Okay, 1.25. And we got, when we did it, for negative, we got 1.2. So that's not very far away. And then f of 0.2 is this, and we got 0.8. So which one is closer? So what was I doing? All right, so let's do the absolute value of this is the exact value minus what we got, which was 1.2, versus the absolute value of this minus this, which is 0.03. So it is better. The approximation at 1.2 is better than the approximation at negative 0.2. The other thing that I would point out here is if we go back, let's go back. Just want to point one thing out. I know I'm taking a lot of your time here. Here we go. I'm going to go back to the graph. The tangent line at 0 will keep being like sort of maybe almost useful between 0 and 1, and also between -1 and 0. But once you go past -1, it's useless because the curve just like outright changes, right? A different branch. Whereas on the right-hand side, it stays on the same branch. So that's like more of a reason to think that it's probably a better estimate as you go to the right than to the left. Vertical asymptotes, infinite discontinuities is their other name. They're weird. They mess up graphs, and they mess up a lot of the things that we do in calculus. So you always have to be looking for them because the curve just behaves really strangely around them, right? It goes to infinity, goes to negative infinity, whatever. All right, I'm going to end this here, and I will come back in another video, and we will keep going. So I will see you then.